All right, so in this worksheet, velocity versus time practice, we're looking at a velocity versus time graph. And whenever you have a graph like this, you can see that the 10 doesn't look like it exactly matches up with that point right there. When it's kind of vague like this and you don't really have increments in between, just assume that that is matching up with 10 and that 10 matches up with 3. So with that being said, let's say, when does the object have a constant velocity? Now, a constant velocity means that you have no acceleration. Remember, for a velocity versus time graph, a slope indicates acceleration. So the parts of the graph where you have a constant velocity are where you have no slope. So that's these 2 points right here. So from 0 to 5 seconds and from 20 to 25 seconds. All right, so you got zero slope, you got constant motion, you got 2 meters per second there, and negative 1 meter per second there. What's the acceleration from 10 to 20 seconds? All right, so from 10 to 20 seconds, the acceleration for a velocity versus time graph, acceleration is equal to the slope, which is the rise over the run, the rise of a run. All right, so looking at this, let's start with up here at 10, go down here to 20 seconds. The rise goes from 3 down to negative 1. All right, so that's 3 down to negative 1. So that's a negative 4 for the rise. And that's another way of doing that is just saying negative 1 minus 3. Negative 1 minus 3 gives me negative 4. And then we divide by the run. The run goes from 10 to 20 seconds. So 20 minus 10, that gives me 10 seconds. So negative 4 over 10, that's negative 0.4 meters per second squared for the acceleration. For part 3, it says, what is the displacement from 10 to 20 seconds? Now, we've already found the acceleration. The acceleration equals negative 0.4 meters per second squared. The next thing is we need to figure out some other information. Well, from 10 to 20 seconds, 10 to 20 seconds gives me a time of 10 seconds. Now that 10 seconds is the difference between those times. It's not this number, it's the difference between 10 and 20. So it's 10 seconds. Some other piece of information we can know from the graph, from 10 seconds to 20 seconds, we know the initial velocity is going to be 3 meters per second. So the initial velocity, 3 meters per second. We also know that the final velocity is going to be negative 1 meter per second. So the final velocity, negative 1 meter per second. All right. And the only thing we don't know is we don't know the displacement. So if you remember our kinematic equations, there are 5 total variables that we could possibly have in those equations. And right now we know 4 of those, and the only thing we don't know is displacement. So what is the displacement? All right, so we could use the final velocity squared equals initial velocity squared plus 2 times acceleration times displacement, because we have everything we need in order to plug in there. And if you did that and you did your math correctly, you would get the right answer. But there's another equation, displacement equals 1/2 times acceleration times time squared plus the initial velocity times time. This will also give me the correct answer. Now, I like this one better because this first one has my displacement buried deep into the equation itself, where I'd have to isolate it. This equation, my displacement's already isolated, so I can just plug in my numbers. So 1/2 times the acceleration, negative 0.4 times time, which is 10 squared, plus the initial velocity, which was 3 meters per second, times the time, which is 10. All right, so half of negative 0.4 is negative 0.2 times 10 squared, that's 100, so that gives me negative 20, negative 20. And then we have 3 times 10, which is 30, so negative 10 plus, negative 20 plus 30, that gives me 10 meters. All right, so just to double check myself, because I do make mistakes sometimes, we got half of negative 0.4 times 10 squared plus 3 times 10, and that gives me 10. So 10 meters, that's my displacement. The last problem, the last question says, from 25 to 27 seconds, is the object speeding up, slowing down, or is it a constant velocity? Well, first off, a constant velocity means that the slope is constantly 0. All right, so from 25 to 27.5. So this range right here. So is it speeding up, slowing down, or changing, or constant velocity? All right, so first off, the slope is upward. And with a slope being upward, that means we have a positive acceleration. And a lot of times students stop right there and they say, oh, positive acceleration, that means it's speeding up. You have to be careful with that, okay? Just because it's a positive acceleration does not mean it's speeding up. There are two ways you can tell whether it's speeding up or slowing down. One is to look at the line itself, and as time moves on, is it getting closer to zero or further from zero? And you can see as time goes from 25 to 27 and a half that it's getting closer to zero. Closer to zero means that it is slowing down. So it's slowing down because it is the velocity is approaching 0 meters per second. So that's one way to tell if it's speeding up or slowing down. The second way is to look at the acceleration and the velocity. Now you'll notice the velocity is below the x-axis, right? So if that line's below the x-axis, that means we're dealing with a negative velocity. Negative velocity. So if we have a positive acceleration and a negative velocity, that also means it's slowing down because velocity and acceleration are opposite. So the velocity and acceleration are opposite. That also means that it's slowing down. Even though the acceleration is positive, that doesn't matter as much as the fact that it's in the opposite direction as velocity.